video we are going to continue to look at projectile motion. So we started looking at projectile motion in the previous video. In that video we looked at a problem of a projectile being fired from the ground at an angle with an initial velocity, and we resolved the initial velocity into its vertical and horizontal components. We're going to take that same problem and look at it in more detail. So the problem was that a particle is fired into the air from the ground with an initial velocity of 2 meters per second at an angle of 60 degrees to the horizontal. So this is a vector, this velocity, because it's 2 meters per second, so that's its magnitude, that's the speed, but it's directed at an angle of 60 degrees, so it's got a direction. So it's a vector, it's a velocity. Now the questions we want to answer in this video are A, what is the maximum height achieved by the particle, and B, what is the total horizontal displacement. So we have done several problems in previous videos looking at motion in one dimension, so something moving backwards and forwards along a straight line in a straight path. Now this is a little different because the projectile is going to take an arc-like motion, so it's going to move along a curve, so it's moving in 2 dimensions. But the initial thing we always do in problems like this is the exact same. We draw a diagram. So let's do that. So we take the ground here, this dotted line is the ground, and this vector represents u, the initial velocity, which has a magnitude of 2. And let's say that the origin is where the particle starts, so where this vector is originating from. And we know this angle is 60 degrees, and we know the path of the particle is going to look something like this. It's going to move in some arc-like motion through the air before landing back on the ground some distance away. So the next thing we do in the one-dimensional case is to write down which variables of the SUVAT variables, which ones we already know, and then think about which ones we want to find out for each question. And we do the exact same thing here. So I've got this table. The only difference, as you'll see, is that for the first 4 we have to have a horizontal and vertical component. So I use subscripts x and y to represent them. So if you take s displacement as an example, we have some displacement in the x direction, but also potentially some displacement in the y direction. So displacement has 2 components, it's a vector, and we have to think about both of them separately. We do that for all the variables except time, because time is just a scalar. So A is concerned with the maximum height, so it's the maximum displacement in the vertical direction. So we only need to think about vertical components of things for A. So let's try and fill this table out, the right hand side of this table where we have the vertical components. So we'll start with displacement, Sy. Do we know what this is? Well, no we don't, because that's what we're asked to find. Then Uy, the vertical component of initial velocity. Well, if you look at the diagram, if I put up these 2 red vectors here, you may remember in the previous video that we introduced these 2 red vectors and then we used trigonometry to find the length of the 2 vectors. And we noted that these 2 lengths are the components of the black vector, which is u. If you haven't seen that video, I suggest you go and watch it. But what we found out was that the vertical component was √3, so √3 meters per second. What about the final velocity? Well, for A, in the vertical direction, the final velocity has a vertical component of 0. So at the point it reaches its maximum height, the particle is still moving overall, but at that exact point it's only moving in the horizontal direction because it's at its maximum height. So it's at the point where it's no longer moving up or down, it's completely stopped in the vertical direction. It was going up, but it was slowing down, going up at a slow and slow rate, so eventually it stopped. Then it's going to start to come back down, and so the vertical component of its velocity would be negative. But for an instant it hits 0, which is just like in the one-dimensional case. If you fire a particle directly up in the air, it'll be slowed down by gravity until eventually it has 0 velocity, and then it'll start to fall back down to the ground. So to find its maximum height, we look at when its vertical component of its velocity is 0. And then what about acceleration? Well, vertical acceleration we know is minus 9.8 ms to the minus 2, because this is the acceleration due to gravity. And in the vertical direction, that's the only thing acting on it. So again, gravity doesn't affect its horizontal acceleration, but it's vertically, the reason it is speeding up or slowing down is just due to gravity. And it's minus 9.8 because gravity is acting down, so we consider the positive direction to be up. So we have minus 9.8. So now what do we do? Well, just like in the one-dimensional case, we've essentially, for this question, we're able to reduce to a one-dimensional case using these variables. I should say that time is something we don't know. For this question, we're not really concerned with time. Maybe later we will be, but for this question we just say, don't know what time is, but we're not really asked about it, so it doesn't matter. So now that we have these variables, we can just do exactly what we do in previous problems and use the Suvat equations. So two-dimensional cases aren't necessarily too much harder than one-dimensional cases once you've figured out the individual components of the variables. So the solution is to find, if you look at my diagram, this height here, this red line, this red arrow, and so we're trying to find it's a displacement. As you can see from our table, we have u, v, and a, and we're trying to find s, or I should say uy, vy, and ay, and we're trying to find sy. So if we remember our Suvat equations, we can use this one, v squared equals u squared plus 2as. Haven't bothered to include the subscript y because this would also apply for the horizontal direction x, so I'm just using a general v, u, a, and s. Now we're trying to find s, so let's just straight away rearrange this equation to make s the subject. So doing that, we would get s equals v squared minus u squared over 2a. And we just have to plug in all the values we have. So we get that sy equals minus 3. Why is it minus 3? Well, v squared is just 0 squared, and then we minus u squared. If u is the square root of 3, then when we square it, we just get 3. So we get 0 minus 3, which is minus 3, and then that's divided by 2 times the acceleration, which is minus 9.8. Simplify this a little bit, we get minus 3 over minus 19.6, which equals 0.15. You could use a calculator for that if you wanted to. So 0.15 meters. So that's the maximum height the particle reaches. So it doesn't get very high. It just gets 0.15 meters in the air before it starts to come back down. So now what do we want to do? Well, if you look back at the diagram, this red line I've drawn going along the ground, this is exactly half the particle's horizontal displacement. So in B, we're asked about horizontal displacement. This is half the displacement because when the particle reaches its maximum point, it's moved half its total distance it's going to move in the horizontal direction. Because in projectile motion problems like this, you always get a symmetrical motion. So this arc is perfectly symmetrical. So when it moves exactly this amount again, so another one of these red lines, we find its total horizontal displacement because this is the point where it falls back onto the ground. So what do we want to do? Well, we want to use this equation, v equals u plus at. But what do we want to use this for? Well, we want to look once again at our vertical components. So we've not even looked at the horizontal components, even though the question is about horizontal displacement. Because using our vertical components, we can find the time the particle takes to reach its maximum height. And why is that helpful? Well, if we find the time the particle rate takes to reach its maximum height, we find the time the particle takes to move half its total distance. Because as we said, it gets this maximum height halfway through its motion. So then, because of the symmetry of this curve, it will take exactly that amount of time again to come back down. So when gravity is the only thing acting on it, it'll go up to the maximum point and come back down from the maximum point in the exact same amount of time, just like in the one-dimensional case. So if we find the time it takes to reach its max point, we find the time it takes to move halfway through its motion, and then we just times that time by 2 to get the time it takes to move all the way through its motion. And once we've got that time, we can hopefully plug it into a Suvat equation to get the displacement. So rearranging the Suvat equation to get time as the subject, we get this: t equals v minus u over a. So to do b, I'm going to call it t sub max. So this means the time it takes to reach its maximum height. And we're just using these vertical components we already have, because we're still just concerned with the maximum height, so the movement in the vertical direction. So we get minus root 3, because it's v minus u, so it's 0 minus root 3, divided by a, which is minus 9.8. That equals roughly 0.18 seconds. So we have 0.18 seconds is the time it takes to reach the maximum height, and therefore move halfway through its maximum, well, its total horizontal displacement. So t final, i.e. the time it takes to finish its motion and settle back on the ground, is twice this. So after 0.18 seconds, it's got right up to the top maximum point on this arc on our diagram. So 0.18 seconds later, it's come back down. So in total, that's 0.36. That's just 2 times 0.18. So that's t final. So now what we want to do is now we need to think about the horizontal components of these various variables, because we need to try and find s sub x, so the horizontal displacement. So let's think about these things in turn. Well, s sub x, if you look at my table, I'm going to say I don't know what that is. That's exactly what I'm trying to find. Now, u sub x, that's its initial velocity, the horizontal component. Again, in the last video, we found this, and it was 1. So again, watch that video, you haven't seen it, but it was 1 meter per second. Vx, we have to say, is something we are not sure of. We don't know what velocity its final velocity will be in the horizontal when it hits the ground, but thankfully we're not really asked about that, so we hope we don't need it. Ax we take to be 0 ms to the minus 2. So we're just saying it doesn't have any acceleration in the horizontal because there's no forces acting on it as far as we're told. It's just fired off at initial velocity, and then we're not told anything about it. So in problems like this, when this is all the information you're given, you always just assume its horizontal acceleration is 0. So we are trying to find s sub x. We have u sub x and a sub x. We also have t at this time, at the time it comes back onto the ground and has moved through its total horizontal displacement. We just said that that happens at 0.36 seconds. So we have u, a, and t, and we're trying to find s. So which Suvat equation do we want? We want s equals ut plus a half at squared. And thankfully s is already the subject here. So we just need to plug in our u, our a, and our t. So when we do that, we get s equals, well, when we plug in the a into the second term, because a is 0, that term disappears. So we only have the u times t term. So we get 1 times 0.36, which equals 0.36. So it's 0.36 meters. So that's the total distance horizontally, total horizontal displacement of the particle. So that's how far away it is from its start point when it crashes back down on the ground.